Okay, so where we ended was looking at our acid-base definitions and some extra ones. So there's a couple things that we kind of want to address here. So let's clean up all the bottom stuff. When we look at acids and bases, we're used to the Arrhenius definition from Gen Chem, pretty much utterly useless in OChem. Okay, so we'll ignore that. The Bronsted Lowry definition works out pretty nicely when we're looking at the transfer of protons. So you should be tying Bronsted Lowry to protons. A proton donor would be something like, I don't know, HCl, which would be giving us H+. A proton acceptor would be, and I totally meant to not write HCl, sorry. What? I meant to write acid. An example would be HCl, which gets us H+. Proton acceptor would be a base, as an example, NaOH. The part of NaOH that makes it a base is the OH, and I would argue we want to avoid saying OH. What's the part that makes it a base? The negative charge. The part that is a base is actually that we have electrons. Hydroxide as a base is true, and it also fits the Bronsted Lowry definition, but that's only for Arrhenius definitions. So we could go through and pick something like NH2. If you said hydroxide is what makes it a base, NH2 minus then is, well, not a base, because it doesn't have hydroxide. But what does NH2 minus have? The negative charge. So it's those electrons that's the biggest part that makes it a proton acceptor, which is really why and where Lewis came into it, because he said, well, the hydroxide definition or even electron donor definition of our proton acceptor, or let's just scratch that and I'll try that again. The Bronsted Lowry definition of a base as a proton acceptor is looking at the atom. And really, if we're trying to draw something out, I don't care necessarily about the atom moving around, but what makes the atom closer or stay affiliated with a different molecule. Well, it's the bond. The bond is defined by the electrons. So Lewis goes through and changes the frame of reference to say that acids are electron acceptors. And if we know what a classical acid is, as the H+, well, what happens in the course of that reaction? The H bonds to the OH. And so what did our acid do? It accepted electrons from the hydroxide. Okay? So we can still use the same definitions or the same general reactions that we've had in all our previous cases. We're just changing the frame of reference. We're changing our opinion, or just the frame of reference. So our electron acceptor is an acid. The electron donor, well, what did hydroxide do? It donated its electrons as a base. So we could go through and refer to all reactions according to the Lewis definition. The problem with that is that applies to so many different things. We want to kind of get a little bit more nuanced so that when we refer to a reaction, we can say, well, this is the type of reaction happening here. And we can look at the reactivity of those species. Okay? And that's where we end up bringing in a new definition. Okay? So I would argue we have our Bronsted Lowry definition, which I would call acids and bases. Okay? So when I say acid, I'm specifically referring to the Bronsted Lowry definition. When I say base, I am specifically referring to a Bronsted Lowry base. I just don't want to say Bronsted Lowry every single time. I could go through and call them Lewis, but that then removes some context of what's happening. Okay, so I want that extra context. The reaction definitions are ultimately the same thing. Okay? They're going to have to go back to the Lewis definition. They can't apply to the Bronsted Lowry. So they apply to the Bronsted Lowry, then they're the same thing. So an electrophile is really just an electron acceptor. which is a Lewis acid. A nucleophile is an electron donor. So we're adding these new words, and everybody tends to trip up and freak out over these. These words mean the exact same thing as electron acceptor and electron donor. Well, that doesn't really make sense. Well, let's take a look at our Greek, I keep doing that, our Greek understanding or our Latin understanding. Phile, P-H-I-L-E, means love. Okay? I don't have a lot of good examples, so I'll just leave those off. You can imagine the other cases where phile shows up and they aren't typically good, one of the first ones that come to mind. Okay? But they're referencing love. To be, and then what is electro? Electron. So an electrophile is something that loves electrons. So it would be accepting electrons. It wants those electrons. So to be an electron acceptor, what characteristic, if I look at a molecule, I'd be like, that's going to be an electron acceptor. What would I expect to see associated with it? A positive charge. Remember, we said the electrophile is a Lewis acid, which is our electron acceptor. Okay? Bronsted Lowry acids are also electron acceptors. So they should fit a similar pattern with the electrophile. What was our Bronsted Lowry acid example? H what? Plus. We're still looking for that same positive charge. So we're finding the positive, and that helps us nail down that we're looking at an acid. Okay? If that positive is affiliated with a hydrogen, we then have an acid. If that positive is affiliated with something other than a hydrogen, that's when we have an electrophile. Okay? What happens when we look at the nucleophile? Well, phile still meant loving. What is nucleo? Nucleus. So nucleus loving. Well, what is a nucleus? Protons and neutrons. Well, neutrons have no charge, so let's ignore those. What are protons? Positive. So to be nucleus loving, okay, what is our characteristic? They love protons. So what does it have to love protons? Negative charge. We scale this back to our Bronsted Lowry definition. What was our classic example of a proton acceptor? OH, negative. All the definitions line up. And because everybody loves Venn diagrams, we've got our Lewis definition, we have our Bronsted Lowry definition, and then we have what I would call the nucleophile, electrophile definitions. Okay? The nucleophile, electrophiles, and Bronsted Lowry are all combined within Lewis definition, but the nucleophile, electrophile are distinct from our Bronsted Lowry. Kind of make sense? Okay. How much of this is review? All of it. Okay. You may regret that later, but let's just stick with that. Okay. Notice within this context, we were using curved arrows to show how things moved. Have we seen curved arrows before? Yes, we saw it when we looked at resonance and moving electrons around within a structure. And I said it was important then. Okay? I clearly thought it was important enough to put on the second exam. And the idea is why?
We need it now.
We need it again. Okay? We're going to...
Bye, boys.
I think it's still there. Maybe.
Do you need some water?
I got some V8. We're still following those same rules. We find a source of electrons and a place that lacks them, and we move them with our curved arrows. Okay? So recognizing the different roles of our arrows is important. That's what this slide shows. Okay? The biggest focus that we will be concerned about, okay, is the full-headed arrow. There are two heads to that arrow as opposed to the fishhook arrow, which only has one head. Why are there two heads to our arrow? We're moving two electrons. What happens if we get rid of one of those heads? We're only moving one electron. Okay? We will see that, but at the end of the semester, that's known as your radical reactions. They become a little bit more challenging to manipulate. So we'll deal with the full-headed arrows. It's the same arrows that we've been using with the same reasons, the same logic behind them. Okay? So curved arrow notation, bond breaking and formation will only involve valence electrons, so we don't worry about core electrons, which is kind of a nuanced thing that we don't worry about. Our curved arrows will show the motion of only those electrons, and that's it. We can use balanced reactions, but we talked about this on Monday. What's the issue with balanced reactions and organic chemistry? Most organic instructors, including myself and textbooks, don't balance the equations. We only look at the organic materials. Okay? So again, I will try my best within most of this unit to make sure the equations are balanced, but you may very well quickly catch me not balancing things. Okay? I can only do the best that I can. So if we take a look at our reactions, we want to add curved arrows to it. We can take advantage of the reactants and the products to help us establish.
I'm just going to steal some chairs.
That's fine. On our balancing process. That's a lot of chairs. So, what changed?
The H got donated to
What H?
the H on that one.
This H?
No, other H.
Muhammad, what are you saying? Why does it not matter?
Those are all the same.
All the hydrogens on that molecule are the same. It doesn't matter which one I take.
Okay.
Right. That H, what happened to it? Donated to the O on the other side. So I understand where you're going with that statement, but we have a bit of a problem there. And of course, they stole your chair. You can yell at Dr. Wood for it. Yeah. The problem with that statement and how Nolan described that, the H was donated, is that if I'm now going to add arrows, you're saying the H went over here. What's the problem with that? What does that arrow show the motion of? An atom. If at best we say it's showing the motion of the electrons, we're taking the electrons in that bond and sharing them over that way. Well, that becomes extra problematic because why? The octet on the receiving oxygen becomes exceeded, and the octet on the starting atom becomes uber deficient. Okay? So we need to make sure that when we're showing our curved arrows, we show the motion of the electrons. So let's change our perspective on how we need to describe this. So while I like Nolan's description of showing the hydrogen move, that doesn't work as well for us. So change the description. What's happening?
The electrons are moving to the hydrogen.
The electrons are moving to the hydrogen?
Sorry, the electrons are moving. Oh, the valence, the empty valence. Those, yeah, those two are moving.
What are those electrons? The lone pair electrons
That's
on
the word I was looking for, on the oxygen.
the oxygen
Move to the hydrogen.
move. Whoa, the
Draw
heck?
an arrow to the hydrogen. Boom.
Move to the hydrogen. So that means we're taking the electrons off of the oxygen and putting them on the hydrogen? They're sharing. Okay, and this is kind of, again, trying to process through what this shows. That's a sharing of electrons there, which means really what are we making with that arrow? A bond. That bond we're seeing in our product. We're not drawing the bond in our reactant. We're drawing the result of that bond formation as a product. Same deal as we did with resonance. Kind of make sense?
Yes. And you're gonna draw the.
Okay, but now what's the problem? Did I accurately show the result?
No.
What's the problem?
The bond from the hydrogen to the oxygen that we just had needs to go to the oxygen.
That hydrogen has now exceeded its octet. We'll take the electrons in the bond between the oxygen and the hydrogen, and we'll share them with the oxygen, or give them to the oxygen. The result is we have an extra lone pair on the oxygen, and we've now lost the bond between the hydrogen and the oxygen. Why did we lose it? Well, there's no more electrons there. We moved them somewhere else. Make sense?
Yes.
So our arrow pushing is there to tell us what to do. Okay? So when you get graded, there's two things now getting graded. What are the arrows you're showing, and what are the products you're showing? Some people were good at drawing the products of resonance, but had no clue what was going on with the arrows. You're now getting graded on both. Okay? Where this is going to become more important is as we scale up in difficulty in questions, you'll stop being able to predict products. You won't know. And if you don't know where you're going, then you need a method to get you there. That's the point of the curved arrows. Okay? What happens in the bottom problem? Say that again?
The double bond breaks and gives the electrons to bromine.
The double bond breaks?
Or
I,
no. Between.
you mean the sigma bond?
No. The way. With the half arrows. Wait, are those?
Okay. I hear where you're going. Half arrows. So you want to do this.
No.
We're taking the electrons in that bond. How many electrons are in a bond? Two. You're giving one to the bromine and one to the carbon. What would the resulting drawing look like? Radicals. We'd have unpaired electrons. Okay? That is a valid maneuver in general, but is that what's being shown? No. What happened to the bromine when we compare it from the reactant to the product? It's not sharing a pair of electrons. So I will take the electrons in that bond and I will give them to the bromine. So we start the arrow in the bond and we move it going to the bromine atom. What is the result? Well, bromine now has an extra pair of electrons. Because it picked up an extra pair of electrons, what happens to its formal charge? It's negative. Nearly everybody will get that one. Because you're like, oh, I'm moving electrons. It gained electrons. It's negative. But what do most people forget? Most students will draw that as a result. What happened? Okay. That carbon is now magically gained a hydrogen. Okay. If we look at what that arrow means, whoa. That arrow means that the bromine gained an electron, but at the same time, that carbon lost an electron, which means that carbon must become positive. Make sense? Now what happens? Now the CN connects. Okay, so I take a lone pair from the CN and I share it with that positive charge. Which electrons should I share?
Either one.
If I take the ones closest to the nitrogen, those lone pairs are belonging to the nitrogen, which means the bond I'm forming is between the carbon and nitrogen. What does this notation show?
Carbon to carbon.
A carbon to carbon bond. That arrow is not valid. Okay, so some people in office hours have been showing structures, and sorry Tristan, I'm just going to use yours as an example, like that, to show the compound H2CO3. While I know what you're trying to say, what does that structure show? A bond between the carbon, well that's supposed to be a hydrogen, and the hydrogen, meaning the hydrogen now has two bonds. Can hydrogen have two bonds? No, so the structure you've drawn is now invalid. Okay? It is very important the order in which you include your atoms, because that changes the meaning of what's happening, particularly when we're looking at our curved arrows showing those things connect. It has to be written as HO. Kind of make sense? Okay. So we've got curved arrows. Now layer in what we just talked about, acids and bases. In the very first reaction, what does that first species act as?
Acid-base.
The reaction, I agree, is an acid-base reaction because what was the overall result? Transfer of a hydrogen. Okay, so yes, labeling this as acid-base makes sense. Okay, but what did that first species act as? The acid or the base? It acted as the base because what happened? It accepted a proton or donated electrons. Okay, because we're looking at the transfer of a proton, I would call this a base, though officially it's a Bronsted Lowry base. What does that mean the next species acted as? An acid, because it donated a proton or accepted electrons, officially known as a Bronsted Lowry acid. Bronsted Lowry is a big long word or series of words. So I don't like memorizing that, and I'll just refer to them as acids and bases. This is distinctly different from other chemistry instructors. Okay, they tend to refer to acids and bases by the Lewis definition. Okay. Could I call that base a nucleophile?
Yes. No, your face is saying yes.
Good. That's exactly what I wanted my face to do.
I'm going to go with yes.
No.
When do we use the nucleophile electrophile definition?
There's no hydrogen.
When there's no hydrogen. What is this base doing? Sharing electrons to hydrogen. Does the nucleophile definition apply well? No. We should not be calling that a nucleophile. Okay? We could call it a Lewis base, but calling it a nucleophile is bad. How about in the bottom reaction? We'll look at the bottom middle reaction where you have these two species, the cyanide and our cyclopentadiene cation. What type of reaction is that? So it's a coordination mechanism, okay? And that was actually sort of intentionally mean question to ask. Okay? You're really only aware of one type of chemical reaction, acid-base.
Yes.
Is this acid-base? Acid-base, according to our definition, is just the transfer of hydrogen. Are we transferring hydrogen? No, so it doesn't fit our acid-base definition. So where did Muhammad go? Muhammad said, well, that mechanistic step is a coordination. I didn't ask for the mechanistic step, I asked for the reaction. What's the issue? You don't know the reaction yet. The reaction is officially a substitution reaction, beginning to end. Okay? So let's look closer at it. Let's label those reagents. What did they act as in each of those steps, or in that step? Since it's not an acid-base reaction, what definition should I not use? Bronsted Lowry shouldn't show up. I could use Lewis, but again, too broad. Go to nucleophile electrophile.
The ring is an electrophile and the seam is
So we're saying the ring is an electrophile because it did what?
got the electron.
It accepted electrons, and the other one is a because
Accepted the proton.
it accepted the proton.
One is a proton. It donated electron.
It donated electrons. I like how you're cycling through the definitions. Okay, you're at least trying them, you're saying them and realizing you're wrong, which is helpful. If you can state it, you can then question your own statement. If you don't make that statement and keep it in your head, you will get it wrong. Okay, put the information down, write it out. Okay, so we've got now different definitions that we can apply through. We're using our curved arrows to help us manipulate through it. Kind of, sort of? Sort of, kind of. That works. Resonance and mechanisms. Okay, in resonance, okay, all of these are showing curved arrows. We find a source of electrons. Our source of electrons can either be a lone pair, okay, or a pi bond. Okay? Those are our good sources of electrons. We will then move them from that source to some place that is lacking them, or some place that is reactive. Okay? In so doing, in the case of resonance, we just say, well, did I draw a valid structure? Right? If yes, then I'm done. If it wasn't valid, that's where we'd move into rule 3. If an octet was exceeded, we could break pi bonds by moving electrons away. What happens in the case of a mechanism? Okay, well, we're still finding a source. Lone pairs and pi bonds are a good thing to start with. Okay, and we'll move electrons towards a chosen atom. That chosen atom should be electron deficient, just like in the resonance. Where we run into an issue is that we'll check our octet. Okay, the very first thing we'll do is break the pi bond. Why would I break a pi bond?
Electrons?
Two answers. What'd you say?
Is it to get electrons?
And electrons, what'd you say? Pi bonds are easy to break. Okay. So when the electrons come in and we exceed our octet, we'll break our pi bond. That gives us more electrons. So we're kind of both right. But now what do we do with those more electrons? Okay. If we've exceeded an octet, we have to break a bond. We'll break the pi bond first because it is the highest energy bond. Why is the pi bond the highest energy bond? It has to do with our hybridization. We're looking at p orbitals versus hybrid orbitals that involve s orbitals. P orbitals are further from the nucleus. They are by definition higher in energy than our s orbitals. So orbitals that involve p, or bonds that involve p orbitals, are higher in energy. So we break those first. If we don't have a choice, there's no pi bond to break, then we will break a sigma bond. Right? The fun question becomes is, well, what sigma bond do I then break? And that's where we run into kind of questions. So let's take a look, starting with the one shown here. What do you think we're going to be doing? Resonance or mechanism? Why resonance? A mechanism is looking at a reaction. Typically in a reaction, what do we have? Two things. How many things are shown? One, which means more than likely we're looking at resonance. Step one, what do we find?
Find a source.
Source of electrons. Where are there electrons?
Lone pair of pi bond.
Lone pair on the oxygens. Pi bond between the oxygen and the nitrogen. Lone pair on the carbon. There are 4 sources of electrons. Which electrons should you do to find your resonance? Every single one of them. Okay. And I can't stress that enough. Okay. It's what we talked about at the very beginning in Unit 1, said you have to test these. You have to be able to find them. Because by doing that practice, what you will find is some of those make absolutely no sense to move. Until you've done the practice and proved that you end in a dead end or with an invalid structure, you're just guessing. In first semester, maybe you're guessing between 2 things. 50-50 shot, you're like, hey, I got it right half the time. I could just guess. Okay? The half the time you'll get it wrong will be when it counts the most on the final. Stop guessing. Draw them all out. Okay? If you've talked to any of my former students, what I tell them is draw it out. Did you draw the structure? If you didn't draw the structure, that's going to be your first step. Because by drawing it, you can then analyze and say, oh, that was stupid. Okay? If you do it in your head, you will get it wrong. So let's start. I'm going to move the electrons up on that oxygen. Where can I move them? They're on the oxygen. There is only, and I have to move them in resonance towards a bond. I'm on an atom. I can only go to a bond. That's it. Only choice. And because it's oxygen, there's only one bond. So, draw the result. I did nothing to the carbon, so I will leave it alone. Because I did something to both the oxygen and the nitrogen, I won't finish them out. I'll now go back and evaluate them. What happened to the oxygen? I had a triple bond, okay. I don't care necessarily that it has a triple bond. I care about its charge. It became positively charged. What happened to the nitrogen? It exceeded its octet. There's 2, 4, 6, 8, 10 electrons around that, 2 in each of those bonds. Exceeding the octet in and of itself is not a problem. Okay? The issue is now fixing it. This structure is invalid. Now that I've got it drawn, I can say, well, how could I possibly fix this? My octet is exceeded, I will break a pi bond by moving the electrons away. What choices of pi bonds do I have around that nitrogen? There's 2 of them, both of them in the exact same position. I need to move those electrons away from the atom that exceeded its octet. They need to move away from the nitrogen. It's got to go, say that again louder, back up to the oxygen. I cannot add arrows to this structure. Why can I not add arrows to the structure that I've drawn? It's wrong. It doesn't exist. But by drawing it, I've now seen where my electrons need to move to account for it. So I will go back to my original structure and say, well, I had a pi bond, I will move them up there. Now I will draw the result of my arrow pushing. Clearly you did not draw it because you said that answer too fast. What did I draw? The exact same thing. What does that mean about using the lone pair electrons on the oxygen for resonance? They don't resonate. The negative answer is useful. You have to process those negative answers. Okay? By going through and continuing to propagate this out, you will go through and test, and you will find that the best resonance is going to be taking the lone pairs on the carbon instead of any of the others. Why should I have started at the carbon and not at the oxygen or the pi bond? Oxygen lone pair is definitely as equally visible as the carbon, so I don't accept see it better.
The negative charge on carbon.
Find the most reactive thing in the structure. Okay? Electrons was our most reactive thing. What is more reactive than just a group of electrons? A negatively charged group of electrons. Those electrons make the most sense to move. Where can I move them? I would argue you have 3 places to move them. 1, 2, 3. Of those 3, by drawing out the results, what you will find is only one of them was valid. The one that was valid is the blue one. What is the result of that arrow pushing? I now have a double bond between the carbon and the nitrogen. We move to rule 3, verify that our octets are satisfied. We haven't exceeded anything. What does it look like? Nitrogen has been exceeded. That is a problem. So this structure is invalid, but I can use it to help me decide where my extra bond or arrow should be. I need to break a pi bond. Where is there a pi bond around that nitrogen? Between the nitrogen and the oxygen and the nitrogen and the carbon. If I move the pi bond between the nitrogen and the carbon, where would I move it? Back to the carbon, which takes me backwards. So that's not helpful. Let's try the other one. What happens if I take the electrons in that bond, which would be this bond, and move them to the oxygen? What is the result? Whoa. Does the nitrogen exceed its octet? No. Did the oxygen exceed its octet? No. Everything's fine. Now we can evaluate and finalize our structure, which means going through and calculating formal charge. What happened to the carbon in the process of this reaction? Became neutral. How could we see that? It started negative, and what did it do? It shared those electrons with something else, meaning it lost negative. If it was negative and lost negative, that would be neutral. What happened to the nitrogen? Well, it gained electrons. So if it was positive and gained electrons, it should go positive, and it gained an electron. It should go neutral. There's 0 in the middle. What's the next arrow show? It lost an electron. So it went to neutral, and then it lost an electron, so it goes right back to where it started. It needs to be positive. Nitrogen did not change. What happened to the oxygen? It gained electrons, it became negative. What do you guys think? Okay, now the fun Unit 1 review. Which of those structures is better? Why is the second one better than the first? We have to evaluate what makes both of them bad. What makes both of them bad? Charges. Positive charge is the same in both cases, so I don't worry about it. The negative charge, different in both cases. I can now compare them. Where do I want the negative charge? Why do I want it on the oxygen? It's more electronegative than the carbon. The second structure is the better Lewis structure. Okay? So we can evaluate each of those stages all the way through. Is this too slow of a review? No. Nick, what's up?
Couldn't we move the pi bond between the nitrogen and carbon and onto the nitrogen and give it a free pair of electrons?
So you're saying once you are here trying to do this?
Yeah.
Theoretically, yes. That's going to be a bit of a mess. Why would that be a bit of a mess? Won't be an octet. Carbon will gain a charge. So there's your octet. Carbon gains a charge by being under on its octet. So that's now technically a bad structure. Okay. The other issue, that nitrogen becomes neutral. What is next to that nitrogen? A negative charge. Which is going to be more stable, to have the negative charge next to a neutral structure, the negative charge next to a positive? Next to a positive, because we can cancel those charges. Okay. Mechanism. We did this already. We find a source. So let's take a look at the structure drawn on the left. Where do we have a source of electrons? On the bromine. So we could try and move those electrons inwards. Okay. What ends up happening? Carbon would exceed the octet. We'd have to move the electrons right back. So we can't move the electrons on the bromine. What else could we do? What's that?
Move the electrons from the bond to the bromine.
What bond?
The carbon to the bromine.
Why the carbon to the bromine bond? Isn't that a sigma bond? Am I allowed to break sigma bonds? Why? Pi bonds are absolutely easier to break than sigma.
That would give charges that you
What's that? Okay, what happens? Whoa. What happens if we tried to break those pi electrons? Okay, we move those electrons to some place that is lacking electrons. Where is there some place lacking electrons? I disagree. There is a place lacking electrons. Positive charge is in the product, so I can't look at that because that's not there yet.
The carbon, which is attached to bromine, that is
Why is the carbon attached to the bromine positive? Bromine is electronegative, withdrawing electron density from that carbon, making that carbon partially positive. So we could take those pi electrons and we could move them here. What's the result? We would exceed the octet. If we can't do that, in the case of resonance, we'd have to move a pi bond. Okay, well, there's no pi bond that helps us out there. so we can move into breaking a sigma. Why are we allowed to break a sigma? We're not doing resonance. We're doing a chemical reaction. We're allowed to break sigma bonds and chemical reactions. What's the result? Bromine gains that electron, becomes negatively charged, and we do end up with this structure. Right? Everybody see that? We end up with the resonance structure of that. How many resonance structures are there for that one compound?
3.
2, 5.
5. If you can't draw all 5, you should go home and practice. Okay? What happens in the next step? We need to find a source of electrons. Where's our source of electrons in that next step? Either the bromine or the cyanide. If we use the bromine, it goes backwards, so we don't use that. We use the other one. We take our source and we move it towards where it's lacking. Positive charge was lacking. We hook that up. Did we exceed any octets? No. So what does that mean?
Good to go.
Draw the result, we're done. Same basic concepts go into moving these arrows. Okay? So here we go. Here's a little challenge for you. Identify the acidic hydrogen. So look at each of those compounds. Identify the most acidic hydrogen in each of those two molecules, and then compare those two structures. Which of those structures is most acidic? So we'll do it this way because we're going to do some bouncing around here. This side of the classroom. No, you guys are already too vocal. Let's go over here. This side of the classroom. Which one do you guys want to do? Which one do you guys want? Left or right? Fast.
Right.
I heard left first. The left would be this one, right? Okay, so you guys are doing this one. Okay? That means, guess what you guys are doing? The right one. Okay? So you guys get to go through, identify the most acidic hydrogen in each of those structures. Once it's identified, go ahead and let me know. What did we get for an answer? The left side. What did you guys say was the most acidic? Which hydrogen was the most acidic in this structure? The one attached to the oxygen. Right side.
Same thing.
Same thing. Which was the most acidic? Left. Okay, why was the left one the most acidic? So now we have all sorts of fun answers on how to describe this. The functional group on the left is a carboxylic acid. The one on the right is an alcohol. You had the answer from the get-go because in Unit 1 I told you to memorize functional groups. Okay. Number 2, you should know the answer because of Gen Chem, where you discussed ranking strengths of acids and bases. Okay. Number 3, you should have read the textbook already. Did you miss any one of those points?
No. Yes.
Then you should probably fix that. Okay? So let's go through and address. Why is the red hydrogen most acidic in this compound? What happens if we removed that hydrogen? Where would the electrons have gone? To the oxygen, which means that oxygen would be negatively charged. What if I had picked, say, this purple hydrogen down here? Well, why is it hard? That why part is what we need to address. If we remove that hydrogen, where do the electrons in that bond go? To the carbon, making the carbon negatively charged. What does the very last thing on this slide say? Systems will always minimize charge. If I'm looking at acidity, I remove the hydrogen and I'm left with a charged structure. Where is the charge most minimal? On the oxygen or on the carbon? Oxygen, because most electronegative. Okay? I could go through and apply every single hydrogen on there. Most of them were the same. Kind of irritating because I had to draw them all on there, but they were almost all the same. You have to evaluate and look at those. So when some people started to say, well, what about the product? The product helps you decide where your charge has been minimized. The product is not your acid. What is the product? The conjugate base. Okay? So our red one was the most acidic because it stabilized the charge best in the product. What about the purple one? And our purple structure, why did we not look at, say, that blue hydrogen? What would happen if that hydrogen was acidic? We'd have a negative charge on the carbon as opposed to a negative charge on oxygen. Which one is more stable? The oxygen, which means the hydrogen connected to that oxygen was the more acidic. Okay? This is what, let's pause. Resuming the recording. We're always minimizing charge. Why does a nucleus fall apart?
When the structure has too many.
When it's unstable. So how many how many hydrogen atoms are radioactive? Hardly any. How about helium? None. Well, that's interesting. Why are those not radioactive? Their nucleus is very stable. What makes it unstable? When do we have, what's a nuclear radioactive element? Uranium. Why is uranium radioactive? Huge isn't good enough. The amount of positive charge in that nucleus is so massive that we can't add enough neutrons or glue to negate that repulsive force. And so what happens? Some atoms or some protons repulse and we eject and get nuclear radiation. Why is it unwise to stick a fork in the electrical outlet? Why is it shocking you? It's a transfer of electrons from our power station all the way through you and into the ground. Okay? That is an unpleasant experience. Charge is bad, which is why when we're looking at a reaction, they will always go to minimize charge. That is our primary goal. Everything we're doing is about minimizing that charge. So when we look at general chemistry, they'll go through and rank acids and bases. Typically, they only rank acids. And they come up with these rules. Okay? Rule 1, down a column, stronger acids have larger conjugate bases. What? What are they saying? If I compare HF to HBr, if we look at them acting as an acid, they both give up H+. That's pretty useless. They also have F- and Br-. Are F- and Br- different? Yes. There's the difference. I need to identify the difference there. Why do I pick the negative charge? Because I know negative charge is dangerous. I won't look at HF and HBr because they're drawn neutral. It's really hard to see the reactive thing in a neutral species. So we look for the charges. So propagate it out. Look at the charges. F- versus Br-. Which one is more stable? Br- is more stable according to rule number 1. Look at rule number 2. Ignore the across a row, down a column. What does rule number 2 say? Stronger acids have higher electronegativity. Anybody see a conflict there? We use rule number 2. HF is the stronger acid. Fluoride is more electronegative than bromine. We use rule number 1. HBr is the stronger acid. Yes, they conflict with each other. Okay? There is a priority as far as assigning how things work. If you look for your ideal partner, okay, you probably have a list of things that you want for your partner. If the only thing they have is money, but they're just a frog, you might be like, I don't know what's going on with that. Okay? That may not work so well, particularly if I want kids with the genetics of the frog. That doesn't work. Right? So we have to come up with ranking systems, and we establish those ranking systems to manipulate and think through this. In Gen Chem, they just say down a column. Stronger acids have larger conjugate. Well, why the hell does that matter? Rule number 1, minimize charge. What is the difference between fluoride and bromide? And this is where it gets tricky with respect to the column. Size. Fluoride is tiny. Bromide is huge. Remember that fork electrical outlet? Hurt. Electrons, bad. What is the size of an electron on fluoride versus bromide? No difference. So here's our electron in fluoride. There it is. Here's that same electron in bromide. It looks like I did a pretty good job making those the same size. I now tell you you have to stick your hand into one of those circles. Remember, you touch the electron, that's going to hurt. Which one do you stick your hand into? Why the bromide? Less likely to get hurt. The same thing is happening with our atoms. If we can spread that electron over a larger area, the effective charge within that is smaller. If it is smaller, it is then minimizing the charge. Size contributes to our stability. Okay? What happens when we move to rule 2? If we compare, say, HF to H2O. Right? And that can be confusing, so let's just say HO, and then there's something over here. I don't really care what it is, but all I'm looking at is the HO. We'd be looking at H plus and O minus. When I'm looking within a row, what happened to the size of the atom? So there's 2 answers. One answer you learned in Gen Chem. The second answer I said in Unit 1 and said this is important and you need to memorize this. They're about the same. So if the size is the same, Rule 1 doesn't apply when I'm comparing acid strengths between HO and HF. So if I can't use Rule 1, what do I have to do? Use another rule. In that other rule, the stronger acid has the higher electronegativity. Which one is more electronegative, fluoride or oxygen? Fluoride. Why does that stabilize the negative charge better? Well, what does electronegativity mean? The ability to hold bonding electrons. If fluoride holds those electrons better than oxygen, well then H plus is going to fall off a lot more frequently in HF than it will in HO. The other rules that your Gen Chem textbook throws at you, because I think you guys use the same book as I pulled these rules from. Rule 3, HOX becomes more acidic with a higher X electronegativity. Okay? So another thing that I have to memorize. This is why people hate Gen Chem, and this is why people go, oh, there's so much memorization in OChem. You didn't pay attention to Gen Chem. Gen Chem was a hell of a lot worse. Rule 4, HOXON. Okay. It's more acidic with more oxygen. Okay? Those are really useless rules. Right? They're saying, I don't want to explain that they just minimize charge, so I'm just going to make you memorize a bunch of stuff. Okay? This is largely because general chemists didn't understand charge to begin with. Rule 3, stronger acids have conjugate bases with resonance. What did resonance mean? The ability to move electrons from one atom to another. What did I just do to the amount of space that that electron has to occupy? I increased it. Guess what rule 3 is? It's rule 1 with one extra caveat. Rule 1 was only looking at the charge on an atom. Rule 3 is looking at that charge across the molecule. So we will look at atomic effects before we look at molecular effects. Rule 4, known as induction. Hydrogens closer to electronegative elements are more acidic. Why would that be? Well, if there's an electronegative element nearby, what is it doing? Taking electrons, which means the atom next to it is now losing electrons. So we're going, hey, this sucks. So what does it do? Grab electrons from the next atom. That next atom happens to be hydrogen. We now have an acidic hydrogen. Okay? So you're looking at propagating these rules further through the structure. Rule 4 is really just rule 2, but again, applied to the molecule as opposed to the atom. Kind of, sort of? Sort of, kind of. Ah, that would be what a quiz is for. H3O plus versus H2O. H3O is the stronger acid, and of course, we always got to follow that up with why. So, get rid of the hydrogen. What would you end up with? H2O. H2, we get rid of H plus. What do we end up with? I do not accept HO. OH is better. Minus. Our first and primary rule for all acid-base chemistry is minimize charge. Which one of those has the more minimized charge? H2O. Guess which one has the stronger acid? The H3O plus that we started with. Interestingly, that rule wasn't on the previous thing from Gen Chem. I don't know why they leave that one off, but they do. HF versus HCl. Right? We remove, we end up with fluoride and chloride. Where are those located? Okay? In a column, which means we need to be evaluating based off of size. Which one is bigger? Chloride, which makes the chloride more stable, which makes the HCl more acidic. H2O versus H, we already did that one. H2O versus HCOOH. Oh, that's kind of irritating. Yeah, because it's a stupid formula. Stop looking at formulas, draw out the structure. We have H bonded to carbon, bonded to oxygen, hydrogen. And we should now immediately go, oh, well, that one's more acidic because carboxylic acid. Y, telling me the name of it doesn't count. We need a Y. If we remove the hydrogen, we'd end up with okay. Charge. Is the charge different? Negative versus negative? No. Okay, what is the atom holding the charge? Oxygen versus oxygen. Is there a difference in size? Okay, oxygen versus an oxygen. Is there a difference in electronegativity? No. What does that mean we now need to move into? Resonance. Yay! To do resonance, we find our most reactive electrons. Where are most reactive electrons? The oxygen with the negative charge, I conveniently did not show all the electrons. Can I do resonance? Can I move those electrons into the bond? No. So OH has no resonance. What about the other one? Can I move those electrons into here? Carbon exceeds the octet, yes, so that's a pause. But then we can move the pi electrons from the other oxygen up there. Which then means, do we have resonance? Yes. Structure right has resonance, structure left does not. Guess what? Structure right is the more stable species, which makes HCOOH the more acidic. CH4 versus CH3F. Right. Again, structure could come in handy. If we remove one of those hydrogens, become negative. And one of the reasons why I picked this one is, do you like that structure?
No.
Why not? Why does it not look right? Can carbon be negatively charged?
No. It doesn't like to.
Yeah, why does it not like to? It's not very electronegative. It can't stabilize the negative charge well. That does not mean in a comparison that it can't be a stronger acid. Okay? So don't just eliminate questions because you don't like the question. Answer the question. And if we removed that hydrogen, we'd end up with a negatively charged carbon. What is the charge? Negative to negative. Difference? No. Next rule. Size. What's the atom holding the charge? Carbon versus carbon. Same. Electronegativity. Same. Resonance. You don't know? Can we move those electrons?
No.
Okay, so that was bad. How about these? No. How about these? No. Okay, so no resonance there. Can I move these electrons here? Did you say that's awkward? We can't move those electrons there because we would then exceed the octet on the fluoride. Remember the whole not showing lone pair thing? This is again where it comes back to bite us. We have to remember that if we have a halogen with one bond, it has 3 lone pairs. Can I shift those electrons over? No. That is not allowed. And due to where I drew it. So is there a resonance? No. So resonance versus resonance? Nothing that helps us. What do we move to? The last one. An induction effect, which means we look somewhere in the molecule for a difference. So we started at charge, saw no difference. So we moved to the atom, saw no difference. Moved out to the bonds, saw we couldn't do any difference. So we move out to an atom. Hydrogen versus hydrogen. Nothing. Hydrogen versus hydrogen. Fluorine versus hydrogen. Oh, there is a difference. What is that difference? Fluoride is more electronegative and can withdraw the electrons. Some people like to bring in a size argument. Size is irrelevant at this point because the negative charge is not being held on the fluoride. Okay? That fluoride is electronegative, so it's drawing electron density away from the carbon, which then means where do those electrons start to move to? Into the structure. Why are we minimizing charge? Makes it less reactive. The more charged it is, the more reactive it is. We're minimizing charge because all of our reactions go to make something that is less reactive. That's why the reaction works. Okay? So that fluoride, or the CH3F, becomes more acidic because of an inductive effect, which is just a fancy way of saying there's an electronegative atom in that structure sucking electrons away. Make sense? Okay. Yeah, go away. So, system will always minimize charge. So I've got rules kind of summarized out here. Yeah. Notice that these rules don't apply to just acids. These rules will also apply to bases. And this is typically where students freak out in the application of the base, which is really showing up in second semester. First semester, it's primarily acids. Okay? But it's the same rules. Why does everybody freak out and not able to apply to the bases? Well, what makes an acid acidic? It's the stability of the conjugate base. Is the negative charge stable?
No.
If it is stable, what does that mean about the ability to get rid of the H+? It's really easy. So when I'm looking at acid strength, I look for the negative charge that is most stable. Why would I all of a sudden have problems if I use that definition, apply it to bases? So number one, that definition applied to acids. Are bases acids? No. So applying the definition of acids to bases is, yeah, that's going to be problematic. Okay. Number two, let's expand that out. What is our definition of a base? Proton acceptor, but remember, protons don't exist. We need something more than that. An electron donor. So a strong base has what kind of a negative charge? So it can't have a positive negative charge. That doesn't work.
Neutral.
Do I want the negative charge to be more positive or more negative? Let's go back to what we said the base was. What is the definition of a base? An electron donor. Do I want the negative charge in my structure to be more negative or less negative? More negative, because what does the base need to do? Donate electrons. If it is less negative, it can't act as a base because it doesn't have electrons. This is why we run into issues. You're looking at ranking acids versus bases, different definitions. Okay? Don't just say, oh, the rule is that the more stable conjugate base, that means it's better. What is the definition you're running under? You have to apply that definition. The rule sets given here allow you to look at charge. Okay? Minimizing charge. Okay? In the case of an acid, that's probably a good thing. In the case of a base, do we want it to minimize charge? No, in the base we want it to be as strongly negative as possible. We don't want to minimize charge. Atom size. This one is at least written correctly. There's no, what does that mean? It's just an evaluation. What does the atom size mean? Okay? That is the next most important thing to look at. I look at my charge. So really this should be step one, look at charge. Step two, look at atom size. Step three, look at electronegativity. Step four, look at a molecular effect, which I'm putting in quotes as size, also known as resonance. Step five, a molecular effect, which is getting at electronegativity, which is induction. What we're doing is applying those things to evaluate back to the definitions of acids and bases. If you memorize, oh, this is what it means to be a strong acid, guess what? You will be shafted when you're asked to rank bases. Right? Because you didn't apply the rules. It's not rote memorization, it's rule application. And with that,